Alright, in this video we're going to take a look at some organic chemistry nomenclature. We've got a mixed group of organic functional groups in this assignment, and we're asked to name the molecules. So we're given predominantly bond line formulas, and then we're going to try to interpret them, classify the molecule, and then name it. So a good way to do this would be, if you really don't know how to name it, you could just watch with me and I'll discuss it with you. Otherwise, try the molecule yourself and then pause the video and then come back and look at the answer. So the first molecule here, the only thing in there is single bonds and carbons, hydrogens. So this is an alkane. So what I want to do when I'm naming an alkane is find the longest continuous chain of carbons. It looks like it would be something like 1, 2, 3, 4, 5, 6, 7. So 7 carbons in the longest chain. It's got 2 branches, a methyl branch with 1 carbon and an ethyl branch with 2 carbons. We're going to start numbering the parent chain at the end closest to the branch. So we'll start at the right, which makes this the 3rd carbon and this the 4th carbon. So therefore, this molecule, naming the branches alphabetically, ethyl before methyl, this is going to be 3-ethyl, 4-methyl, and then there were 7 carbons in the parent chain, heptane. 3-ethyl, 4-methyl heptane. And notice the use of commas and dashes in the names. The second example, we can see that there's a functional group that jumps out at us. It's the OH group. There's a hydroxyl group. So that means this is an alcohol. So what we'll do is number the longest continuous chain of carbons. 1, 2, 3, 4, 5 carbons. And then we're going to number that parent chain from the end closest to the functional group. So this would be carbon 1. And the hydroxyl group is on carbon 2. There's a methyl branch on carbon 3. So we'll name it as a branched alcohol. So the branch is on carbon 3, 3-methyl. And then there were 5 carbons in that parent chain, and it is an alcohol on carbon number 2. So 5 carbons, it's going to be a type of pentanol. And with the alcohol group on carbon 2, you could say 3-methyl 2-pentanol using the American system, or pentane-2-ol would be the UPAC system. The third molecule here, you can see it has a functional group that jumps out at us at the end of the molecule here, a C double bond OOH. So this would be a carboxylic acid. And so we'll number the carbons. This is carbon 1, closest to the functional group. Carbon 2, 3, 4, 5, 6. There are no branches or anything, so this is just a 6-carbon carboxylic acid. 6 carbons, we would think hexane, but carboxylic acid, hex and oic acid. You drop the E from hexane and you add oic acid. So hexanoic acid. The next example has a double bond as the only distinguishing feature, so this makes it an alkene. It's got 4 carbons, so we're thinking butene. It's got the double bond on the 2nd carbon, so we're going to think but-2-ene, or you could say 2-butene. Now, if we want to look at some geometric isomerism, we notice that the 2 carbons in the double bond, the one on the left has this methyl group coming down, pointing down. The one on the right side of the double bond has a methyl group pointing up. Those 2 methyl groups are going in opposite directions on either side of the double bond, which means this would be the trans isomer. So trans-but-2-ene. The next example has a triple bond in it, so this means we're looking at an alkyne. And we remember that alkynes, if we could just maybe just pause for one moment and go back for talk about bond angles for a minute. If you have only excuse me, only single bonds, so alkanes or these alcohols, whenever you have just single bonds, the carbons there have 4 things attached to them. So this carbon has 2 hydrogens attached and then 2 other carbons attached. So when you have 4 things attached, you are tetrahedral geometry, and so the angle there is 109.5 degrees. All of the angles in there between the bonds are 109.5 degrees, tetrahedral bond angles. Same thing here, these are all 109.5 degree angles. In here, this carbon is involved in a double bond. So the double bond means we don't have 4 things attached here, we've only got 3. You've got the alcohol group, this double bonded oxygen, and then you have the rest of the carbon chain. So when you've only got 3 things attached, there's a double bond involved, the bond angle is now 120 degrees. In grade 12 chemistry, we would say that that's a trigonal planar geometry, not tetrahedral. So down here in the alkene, this bond angle, because there's a double bond attached, would be 120 degrees. In an alkyne, there's now only 2 things attached. This carbon that I've just identified has 2 things attached. It's got a triple bond to this carbon and a single bond to this carbon, which means the bond angle is now 180 degrees, which is why it looks linear. Anyways, let's come back to the nomenclature. This has 3 carbons in it, so we're thinking propane, but it's got a triple bond, so propyne will be its name. There's no ambiguity in terms of where the triple bond is. It's with only 2 bonds. One or the other has to be the triple bond, and whichever one is the triple bond would have been the first bond in the chain, so we don't need to number it. Over here we have an alcohol again. The OH hydroxyl group identifies it as an alcohol. These are all single bonds, so this is all 109.5 degree tetrahedral angles, and that's why there's this zigzaggy pattern to it. So we'll identify the parent chain. This would be carbon 1, carbon 2, 3, 4, 5, 6, 7, 8, 9. There's 9 carbons in the longest chain. The third carbon has the alcohol group, so we'll start maybe by saying nonane, drop the E and add 3-all. So there we've named the alcohol. But now we see some branches. Carbon 4, carbon 5, carbon 7 all have methyl branches attached. So we'll say 4, 5, 7 dash trimethyl nonon 3-all, or 4,5,7 trimethyl 3-nonanol. Notice that this would all be one word. Next, we have a cycloalkane, okay, an alkane ring, so only single bonds, so this was a cycloalkane. This ring has 6 carbons in it, so I'm going to start by saying cyclohexane. Okay, cycloalkanes start with the prefix cyclo in their name, and then it's got this methyl branch, so methyl cyclohexane, and that should really all be one word. Notice we don't need to number it because whichever carbon in the ring has the methyl group attached, that would be considered the first carbon in the ring, so we don't need to number it. The next molecule is an alkene. There's that double bond. So we'll identify the parent chain, carbon 1, 2, 3, 4, and now it doesn't really matter which way we go, 5, 6. So it's a hexene. And now we should say where the double bond is. It's not the first bond, it's the second bond in the molecule. So this would be hex-2-ene. If it were the first or the third bond, we'd have to say hex 1-ene or hex 3-ene. And again, the American system would say 2-hexene here. And now numbering from that same end, carbons, 1, 2, 3, 4, carbon number 4 has this 2-carbon branch, and a 2-carbon branch is ethyl. So we'd say 4-ethyl hex-2-ene. And then finally, if you want to get into the geometric isomerism, looking at the double bond here, we see that this methyl group is coming down towards us while the rest of the molecule is going up away from the double bond. So they're going in opposite directions on either side of the double bond. Therefore, that's the trans isomer again. So trans 4-ethyl hex 2-ene. Notice the numbering. When you were numbering the 2-ene, saying where the double bond is, we're numbering the bonds. So this was the second bond. But when we're numbering where the branches are, we're now numbering carbon atoms. So first, second, third, fourth carbon atom. So the numbering refers to two different things when you're looking at branches or the location of the double or triple bonds. The next molecule, we see an alcohol group again, OH. So this is going to be an alcohol with several branches in it. So it's kind of complicated. Let's identify the parent chain. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to start numbering the parent chain at the end closest to the functional group. So the alcohol is on carbon 3. There's a methyl branch on carbon 5. There's an ethyl branch on carbon 6. There's a methyl branch on carbon 8. So it's a 10-carbon chain with an alcohol group on carbon 3. So we'll start by saying it's decane 3-ol. And now methyl branches, 2 of them, and an ethyl branch. We name the ethyl branch first, alphabetically before methyl. So we're going to end up saying that this was 6-ethyl, carbon 6 has the ethyl branch, dash 5,8 dash dimethyl, and then decane 3-ol. Remember, when alphabetizing the branches, you do not alphabetize by the prefixes. So 2 methyl branches, we said dimethyl, but when we alphabetized, we looked at the E in ethyl and the M in methyl, and we named the ethyl first. The next molecule is a organic halide. It's just an alkane with some halogens attached. So we'll number the parent chain, starting at the end closest to branches. Carbon 1, 2, 3, 4, 5. So it's a pentane. It's got 2 chloro branches, and it's got 1 bromo branch. We'll name the bromo first alphabetically. 2-bromo dash 2, 3 dash dichloro, 2 chlorines, and then pentane. The next molecule, this functional group jumps out at me. There's a carbon with a double bond O and an OH. So this was a carboxyl group, and therefore that's a carboxylic acid molecule. The chain of carbons has 1, 2, 3 carbons. There's no branches. So 3 carbons, I'm thinking propane, but a carboxylic acid, propanoic acid. Drop the E from propane and add oic acid. The next molecule is also a carboxylic acid. It's got this carboxyl group on the right-hand side this time, C double bond O, OH. but it's got a branch as well. So let's number the parent chain. 1, 2, 3, that's carbon 3, 4, 5. So pentane would become pentanoic acid, but it's got a methyl branch on carbon 3. So 3-methyl pentanoic acid. The next example is again an alcohol. The OH jumps out as an alcohol group. We'll start numbering from the end closest to that alcohol group. So this would be carbon 1, carbon 2, carbon 3, carbon 4, the alcohol group. Carbon 5 has a methyl branch, 6, 7, 8, and now it doesn't really matter which way we go, but I'll call this maybe carbon number 9. So carbons 5 and 8 have methyl branches. Carbon 4 has the alcohol group, and there's 9 carbons in all. So putting that together, we'd have 5, 8 dimethyl, and then 9 carbons with the alcohol on carbon 4, nonan 4 all. Next we have an alkene again, a double bond. The parent chain, starting numbering closest to that double bond, we can choose either one of these carbons as the first. So there's carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. So it's a pentene. It's the second bond that has the double bond, so it's a pent-2-ene. And the second carbon has the methyl branch. So 2-methyl pent-2-ene. Now you might wonder, well, what about the cis and trans isomerism that we discussed earlier, the geometric isomerism? Remember that when you have a double bond, you might have to worry about cis and trans isomerism. However, in this particular molecule, this carbon in the double bond has 2 identical things attached. It's got a methyl group going up and a methyl group coming down. The fact that it has 2 identical substituents means that the cis-trans isomerism is destroyed. If I trade the places, these 2 methyl groups, trying to change it from a cis isomer to a trans isomer or vice versa, the molecule doesn't change because these are the same groups. So there is no cis-trans isomerism if one or both carbons in the double bond have identical branches coming off. Next we have an alkyne, triple bond. We'll start numbering from the end closest to the triple bond. Carbon 1, carbon 2, carbon 3, carbon 4, and the third carbon has a methyl branch. The first bond is the triple bond. So we have 4 carbons, butane. It's got a triple bond, butyne. It's the first bond that's a triple bond, but1-ine, and there's a methyl branch on carbon 3. 3-methyl, but1-ine. All right. We've got next another cycloalkane with 2 methyl branches. So this cycloalkane has 5 carbons in the ring, therefore cyclopentane is what I'm thinking. One of these 2 carbons with a branch would have to be carbon 1, and it doesn't matter in this case because they're identical. It doesn't matter which is with the number 1, so I'll call this carbon 1. And then I'm going to number in a direction that would keep the next number, the next branch at a smaller number. So if I number clockwise, 1, 2, 3. So that's carbon 1, and then carbon 3 would have methyls on them. So this is 1, 3 dash dimethyl, and 5 carbon ring cyclopentane. Now, if this diagram were more accurate, it would have used wedges instead of dashed lines for the bonds coming off of the ring, because we remember that in a cycloalkane, every carbon in this ring has two branches. This carbon right now has two hydrogens attached. This carbon has one hydrogen and one methyl. Of the two branches, one comes above the ring, while the other goes below the ring. So we would technically have to worry about whether these two methyl branches were on the same side of the ring, both coming up or both going down below the ring. That would have been called a cis isomer, because they're on the same side of the ring. Or we would have one coming up above the ring, one coming down below the ring, then they're on opposite sides of the ring. That would have been a trans isomer. In this diagram, which is similar to what you'll see on WebAssign or in your Zumdahl chemistry textbook, there aren't any wedges shown, so we don't need to worry about the cis or trans isomerism, at least in the naming of it. The next molecule we see again a triple bond. This is an alkyne with 1, 2, 3, 4, 5, 6 carbons. It's a hexyne, or the second bond is the triple bond, so it's a hex 2-ine, and 1, 2, 3, carbon number 4 has the methyl branch. Notice we're numbering from the end closest to the triple bond. So this is 4-methyl hex 2-ine. 4-methyl hex 2-ine. Next we have a cycloalkane, but with an alcohol group attached. So this would be 4 carbons, cyclobutane, with an alcohol group, cyclobutanol. Alright, the next one is again an alcohol with the OH. We'll number the parent chain closest to the alcohol, so carbon 1, 2, 3, 4, 5, 6, 7, 8. So it's an octanol. In fact, it's 4-octanol, or octan 4-ol. Carbon 3 has a methyl branch. Carbon 6 has an ethyl branch. We name the ethyl before the methyl, so this is 3-ethyl, 6-methyl, octan 4-ol. The next molecule is a carboxylic acid, C double bond O, OH. So we start numbering at that carbon, carbon 1, 2, 3, 4, 5, 6. That would be the longest chain. So third carbon has an ethyl branch with 2 carbons in it. So this is 3-ethyl, 6 carbons in a chain, hexanoic acid. Carboxylic acids always end in oic acid. The next molecule is again an alkene with a double bond in it. We'll number from the end closest to the double bond, so let's check. 1, 2, 3, it would be the 4th bond if we count from the top. 1, 2, 3, 4, it's the 4th bond if we count from the bottom. So now which end should I count from? It looks like it's the same distance from each end. Well, we'll count from the bottom so that now we keep the branch numbers smallest. So the first thing is to count from the end closest to the double bond. If it's a tie like this, from either end, then the second rule would be we want the branch numbers to be smallest. So we're going to count from the bottom, carbon 1, 2, 3, 4, 5, 6, 7, 8. So this is oct 4-ene. The 4th bond is the double bond. Carbons 2 and 3 have methyl branches. So 2, 3 dimethyl, oct 4-ene. And then looking at that double bond, we notice one branch comes up, the other branch comes down, so therefore they're on opposite sides of the double bond. This is trans 2,3-dimethyl oct 4-ene. The next molecules look rather simple, and sometimes those are a little bit harder to name, but in this case they're not that hard. There's one carbon, so we're thinking methane, but this one carbon has 3 chlorines attached. This is an organic halide. So with 3 carbons attached, it would be trichloromethane. Its formula would be CHCl3. The next molecule is also an organic halide with 2 carbons. 2 carbons is ethane. The 2 bromines are both on the first carbon in the chain. There could have been one on one carbon and one on the other carbon, so I'd better number this to be clear. So this is 1, 1. They're on the same carbon and the first carbon in the chain. Dibromo ethane. And again, I'm numbering there because there could have been a 1, 2 dibromoethane. Next we have another cycloalkane. It's 6 carbons in the ring, so cyclohexane. There are no wedges coming off of here. It's using just dashes, so we don't need to worry about cis and trans again. I'll number this as carbon 1, and then this would be 2. This would be carbon 3. They're 1 and 3. So that the 2 branches are both ethyls, so 1, 3 diethyl cyclohexane. Next we've got a single carbon with a double bond OH. So this is a carboxylic acid with 1 carbon. 1 carbon is methane, so therefore this is methanoic acid. A common older name for that was formic acid as well. Next we have an alcohol again, and the alcohol will be on the second carbon in the chain, and there's 4 carbons total in that chain. So that would be, let's see, carbon 3 has a methyl branch, so 3-methyl butan 2-ol. Next we see another alcohol, OH, starting numbering at the end closest to the functional group, carbon 1, 2, 3, 4, 5, 6, 7, 8. There's 8 carbons in all. So this is carbon 6 has 2 methyl branches, 6, 6 dimethyl, and then octane dash 2-ol. The alcohol group is on the second carbon in the octane chain. Next we've got an alkyne again with a triple bond, numbering from the end closest to the triple bond, carbon 1, 2, 3, 4, 5, 6, 7, 8, and now it doesn't matter which way we go, 9, 10. So it's a third bond. Bond 1, 2, 3 is the triple bond, so it's a dec 3-ine. Numbering the carbons, 1, 2, 3, 4, 5, 6, 7, and 8. So carbons 7 and 8 have ethyl branches. Carbon 6 has a methyl branch. We name ethyl before methyl, so we'd have 7, 8 diethyl, 6 methyl, and then there were 10 carbons total, so decane, dec, and then the third bond was the triple bond, so dec 3 ine. It's a triple bond, so it's an alkyne. Next we have another cycloalkane. This one's got only 3 carbons, so this particular cycloalkane is the one that has the greatest amount of ring strain, because the bond angles, which would like to be 109.5 degrees when you have 4 things attached, they've been squeezed down to 60 degrees. So this is a very strained molecule. It's going to be 1, 2, because they're on neighboring carbons, dimethyl cyclopropane. 3 carbons in a ring, cyclopropane. The 2 methyl branches are on neighboring carbons. Those would be carbons 1 and 2. You could have had them on the same carbon, which would have been 1,1-dimethyl cyclopropane. Next we have carboxylic acids, both of these. I can see that from the COOH in them. That's a C double bond OOH. With 2 carbons, CH3COOH, this would be ethanoic acid, also known as acetic acid. And the next one has 4 carbons, C3 and then the COOH, so butanoic acid. Okay, let's keep going. We've got an alcohol group next. This is an alcohol. It's on the 2nd carbon. 1, 2, 3, 4, 5, 6 carbons in the chain. This is hexane 2-ol. Now, for the first time, we're seeing an aromatic hydrocarbon. Aromatic hydrocarbons have benzene rings in them. A benzene ring is a 6-carbon ring, similar to cyclohexane in that way, but instead of having just single bonds, it has a conjugated system of single and double bonds. So it's called an aromatic compound, and specifically this ring is a benzene ring. This particular benzene ring has 2 chlorines attached, so we could call this carbon 1, carbon 3. You could call this 1,3 dichlorobenzene. Now another system uses prefixes. If you have branches in benzene, and this only applies to benzene, if you have 2 branches side by side, so 1, 2, you could have called that orthodichlorobenzene. When you have 1, 3, the branches are now separated by a carbon in the middle. This could have been called metadichlorobenzene. If they're on opposite sides of the benzene ring, so 1, 4 dichlorobenzene, it would have been also known as para-dichlorobenzene, or PDB. The next molecule is again a cycloalkane, but it's got an alcohol group, and this time the bonds are shown with their geometry with wedges. So this wedge is a solid wedge. It means the alcohol group is coming up out of the paper towards us. This wedge is a dashed wedge, so it means the methyl group is going down below the paper away from us. So this is to communicate that the 2 branches are on opposite sides of the ring. So what we'll do is we'll number the alcohol group carbon 1. It'll take priority over the methyl group. That's the functional group of an alcohol. Carbon 2, carbon 3 is the methyl branch. So because they're on opposite sides of the ring, I'll start by saying trans 3-methyl, and then cyclohexane becomes cyclohexanol. So trans 3-methyl cyclohexanol. We don't need to say 1-cyclohexanol or cyclohexane 1-ol, because it would be understood that the first carbon in the ring was the one with the alcohol group. Now, for the first time, we're seeing a carbonyl group. Excuse me, a carbonyl group. C double bond O, and it's in the middle of a chain. It's not at the end. So therefore, this is a ketone molecule. First time we've seen this. Carbon 1, 2, 3, 4, 5, 6, 7, 8. So this is an octane 3-one. Ketones are named like that. It's saying 3-one because the third carbon is where the ketone group is. Carbon 5 has an ethyl branch. Carbon 6 has a methyl branch. So 5-ethyl, 6-methyl, octane 3-one. Ethyl before methyl alphabetically. Next we have a carboxylic acid, COOH, with 1, 2, 3 carbons, so therefore propanoic acid. Propane has 3 carbons. Carboxylic acid, you drop the E from the ending and you add oic acid. The next molecule has what looks to be a carboxyl group, C double bond O, but instead of OH, we see OR. Therefore, this is actually an ester molecule. We know that esters were made from alcohols, and the alcohol would have been the part bonded to the O, and then they're also made from carboxylic acids, which would be this part up here. So we name the alcohol portion first, 2 carbons, so that would be ethyl, and then we name the rest 1, 2, 3, 4 carbons, so butanoate. Okay, the ending for an ester is oate. So ethyl, because this piece down here bonded to oxygen had 2 carbons. Butanoate, because the remaining molecule had 1, 2, 3, 4 carbons in it. Next we see an ether, oxygen with 2 R groups attached. The R group on the right is an ethyl group. The one on the left is a 1, 2, 3, 4 butyl group. So we'll name alphabetically butyl, ethyl, ether. Next we see another aromatic hydrocarbon, a benzene ring with 2 bromine substituents. They're on neighboring carbons, so we could say 1, 2 dibromo benzene. Or, when they're side by side like that, you could have said ortho dibromobenzene. Next we have a cyclopentene molecule. So we have cyclopentane ring with a double bond. It's cyclopentene. The 2 carbons in that double bond would have to be numbered 1 and 2. So I'm going to number them like this, 1, 2, in order to keep the branch numbers smaller. So 1, 2, 3, 4. So it's a 5-member ring with branches on carbons 3 and 4, and the double bond as I've shown. So we'll name the ethyl branch first. So 4-ethyl, 3-methyl, cyclopentene. Now notice we don't need to number where the double bond is because it's assumed to be the bond between carbons 1 and 2. And then notice that the branches, one has a dashed wedge, so that methyl branch is going below the paper, below the ring. The other has a wedge, an open wedge, so that a solid wedge if you like. So that means that that bond is coming out of the paper towards us. They're on opposite sides of the ring. This was the trans isomer. Trans 4-ethyl, 3-methyl cyclopentene. Next we have a carboxylic acid, C double bond O, OH. It's got 1, 2, 3, 4, 5 carbons. It's a pentanoic acid. And on the third and fourth carbons in the ring, in the chain, there's methyl branches. So it's 3, 4, dimethyl pentanoic acid. Next we have an ester, C double bond O, OR. That's an ester. The part bonded to the oxygen here gets named first. So methyl. And then the rest of it had 1, 2, 3, 4 carbons. So methyl butanoate. Next we see a ketone. It's got a carbonyl group, C double bond O, in the center of a chain. It's a 3-carbon chain, so propane would become propanone. You don't need to number where the ketone is, because if you've only got 3 carbons, the carbonyl would have to be in the middle carbon if it's a ketone. Remember that in ketones, the carbonyl is never at the end of the chain. If it's at the end, it's called an aldehyde, and the name would have been propanal. Next we have 4-carbon rings, so this is cyclobutane with an alcohol attached, cyclobutanol. We now have an aldehyde. The carbon at the end has the carbonyl group. When you have a carbonyl terminal at the end of a chain, that's an aldehyde. It's got 1, 2, 3, 4, 5 carbons, so this is pentanal. Pentanal. You drop the E, you add Al for an aldehyde. There's no need to number, because in an aldehyde the carbonyl is assumed to be at the end of the chain. Has to be at the end of the chain. Next we have an alkene. Let's find the longest chain, starting at the end closest to the double bond. 1, 2, 3, 4, 5, 6, 7, 8, 6, 7, 8. It doesn't matter which way we go. It's going to be an octane-related molecule. The second bond is the double bond, so it's oct2ene. 1, 2, 3, the fourth carbon and the fifth carbon have branches. We have a propyl branch, 3 carbons, and we have a methyl branch. Naming them alphabetically, we'd have 4 methyl, 5 propyl, oct2ene, and looking at the double bond, 1 branch comes up, 1 branch comes down below the double bond. This is the trans isomer. Okay, we haven't seen it yet, but if they're on the same side of the double bond, it's a cis isomer. Last page. So we have a cycloalkane, specifically cyclopropane, with 2 methyl branches on the first carbon. So this would be 1,1-dimethyl cyclopropane. We have to say 1,1 because there could have been a 1,2. Could have been on neighboring carbons. We don't need to say cis or trans, because if you have 2 branches on the same carbon in a ring, they have to be on opposite sides of the ring. There couldn't be a cis isomer when the 2 branches are on the same carbon of a ring. If those 2 branches were on 2 neighboring carbons, then we'd have to say cis if they're on the same side, or trans if they're on opposite side of the ring. Next we have an alkyne with 1, 2, 3, 4, 5, 6, 7 carbons. So it's going to be The first bond is the triple bond, so it's a Hept1-ine. And then 1, 2, 3, 4, 5, 6. We have 4 methyl branches. So 3, 4, 5, 6, tetra, methyl, and then there were 7 carbons, so Hept1-ine. And remember, when there's a triple bond involved, the bond angle is 180 degrees. When there's only single bonds, 109.5 degrees. If there's a double bond, 120 degrees. Next we have a cycloalkene again. It's a cyclohexene, numbering the 2 carbons in the double bond as carbons 1 and 2, and numbering them in a way that keeps the branch number smallest. I think I would do 1, 2, 3, 4. 1, 2, 3, 4. Yeah, that's the way to keep the branch number smallest. So this would be 4-chloro cyclohexene. Again, you don't need to say cyclohex-1-ene because the carbons 1 and 2 would be assumed to be on either side of the double bond. Next we have an aldehyde again. Aldehydes have carbonyl groups, C double bond O, at the end of the chain. So carbon 1, 2, 3, 4, 5. This is pentanal, Al, with 1, 2, 3. There's a methyl branch on the 3rd carbon. Number from the end closest to the aldehyde. So that would be 3-methyl pentanal. Next we have a carboxylic acid, COOH. This is carbon 1, 2, 3, 4, 5, 6, 7. So it's a heptanoic acid, and carbon 1, 2, 3, 4 has an ethyl branch attached, 2-carbon branch. So 4-ethyl heptanoic acid. Next we see a benzene ring again, that 6-carbon ring with alternating single and double bonds. So this is an aromatic hydrocarbon. It's got 3 branches, 3 fluorines on carbons 1, 2, 3, and 4. So carbons 1, 2, and 4. There are no prefixes for this, like ortho, meta, para. Those only apply when there's 2 branches. So we'll call this 1, 2, 4 trifluoro benzene. The benzene ring is always at the heart of aromatic hydrocarbons. Next we've got an ether. An ether because we see this oxygen with 2 R groups attached. One R group is a methyl branch. It's only got 1 carbon. The other R group has 1, 2, 3, 4, 5 carbons. It's a pentyl group. We'll name them alphabetically. So methyl pentyl ether. Next we have a carbonyl group in the middle of a chain. So this is ketone. The carbonyl group looks like it's in the very center of the chain. So I'll number 1, 2, 3, 4, 5. So it's the 3rd carbon in a 5-carbon chain. So this would be pentan 3-one. It's a ketone with the carbonyl at the 3rd carbon. Next we have an ester again. C double bond O, OR. The R group attached to the O came from an alcohol, and in this case 2 carbons. The alcohol was ethanol. and the rest of the molecule has 1, 2, 3, 4, 5, 6 carbons, so it was the ethanol molecule reacting with hexanoic acid as a carboxylic acid. The name of the ester, we name this first, is ethyl, and hexanoic acid would become hexanoate when you have an ester. Ethyl hexanoate. And the next molecule is a diene. It's got 2 double bonds. So notice there's no branches, and we're not going to worry about cis or trans isomerism here. So carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 10 carbons, so I start with decane in my head. The second bond and the fourth bond are double bonds. So dec 2, 4, diene would be the name. Next we have a cycloalkane with an alcohol group attached. 2 solid wedges means these 2 branches are coming up towards us on the same side of the ring, so it's going to be a cis isomer. The alcohol group would be attached to carbon 1 in the ring, takes priority, so the methyl branch is carbon 2 attached to carbon 2. So this would be cis 2-methyl cyclopentanol. Cis because the 2 branches are on the same side of the ring, and cyclopentanol because the 5 carbons formed a ring, cyclopentane. Next we have an alkyne again, triple bond, 1, 2, 3, 4, 5, 6, 7 carbons. So it's a heptyne. It's the second bond, so heptyne, that's the triple bond. Carbon number 1, 2, 3, 4 has a methyl branch. So this would be 4-methyl heptyne. And the last 3 examples. We have a carboxylic acid again, COOH, with 1, 2, 3, 4, 5, 6, 7, 8 carbons. So it's an octanoic acid, but carbon 3, 4, 5, 6, 3 and 6 have methyl branches. So 3, 6, dimethyl octanoic acid. Carboxylic acids, you drop the E from octane and you add oic acid. Next we see an ether, oxygen with 2 R groups attached, and these R groups look identical. They have 1, 2, 3 carbons each. 3 carbons is propyl, so this would be dipropyl ether. And finally, we have what looks to be just a branched alkane. I don't see any special functional groups, so it's just an alkane with 1, 2, 3, 4, 5, 6, 7, 8 carbons, I think. 1, 2, 3, 4, 5, 6, 7, 8 carbons in the longest chain. Numbering from the end closest to a branch, 1, 2, 3. Carbon 3 has 2 methyl branches, and carbon 5 has a propyl branch, 3 carbon branch. So putting them alphabetically, this would be 3, 3 dimethyl dash 5 propyl, 5, 6, 7, 8 carbons octane. 3, 3 dimethyl 5 propyl octane. So there you have it. That's quite a number of mixed organic chemistry functional groups looking at alkanes, alkenes, alkynes, cycloalkanes, aromatic benzene derivative molecules, alcohols, ethers, carboxylic acids, and esters. There are certainly more complicated examples than the ones we've looked at, but that's a good variety right there.